Hello and welcome to MT3. We are still on the series solution, and this time we're going to look at a particular example in some detail. We're going to look at Bessel's equation. Now this is discussed in Arfken, Weber and Harris chapter 7 and in Riley, Hobson and Benz chapter 18.5, which is a chapter where Riley's book discusses all kinds of special functions, and Bessel's equation gives you the Bessel's functions, which is one class of important functions in mathematical physics. So here's what Bessel's equation looks like. X squared times y double prime plus x times y prime. This part looks like a nice Euler equation, but this part is not. So then we have plus x squared minus n squared, n is some constant, times y is 0. Now this ordinary differential equation arises when solving Laplace's equation and the Helmholtz equation. You'll see these when we look at partial differential equations. When we try and solve these equations in spherical or cylindrical coordinates, then you will end up with Bessel's equation. And therefore it's, we need to know how to solve Bessel's equation. So the very first thing you should do is, by the way, this is Friedrich Wilhelm Bessel, if you wanted to see. So come back to his equation. The very first thing we want to do is to find the singular points of this equation. And so we put it down in its regular form, standard form, which would involve having the y double prime, the highest derivative, appearing with a unit constant. So we have to divide by x squared. So we have y double prime plus 1 over x, y prime, plus in brackets 1 minus n squared over x squared, close brackets, y is 0. And this lets us define p of x as 1 over x. This is the function before the y prime. And q of x, which is the function before the y, as 1 minus n squared over x squared. Now both of these are divergent as x tends to 0. So x naught is equal to 0 is a singular point. We know that. The next question is it going to be a regular or irregular singular point? And so we do the standard recipe. You multiply p of x with x minus x naught, where x naught is 0, and that just gives you a 1, because you'll have an x times 1 over x, which is 1. This is well behaved, as x tends to x naught is equal to 0. So that's good. And then we have to find out what happens to q of x. So we multiply it by x minus x naught squared, which is simply x squared, and that will give us an x squared minus n squared, which is simply tends to minus n squared, which is well behaved as x tends to x naught, which is equal to 0, and therefore x naught is equal to 0 is a regular singular point. Okay, good. And that's good because we are going to perform use a Frobenius expansion about x naught is equal to 0. And the fact that it's a regular singular point is good. So Fuchs theorem. What does Fuchs theorem say? Well, it says that if x naught is a regular singular point, then at least one series solution about x naught is equal to 0 will be possible. But we need the Indicial equation to tell us more. We need the Indicial equation to tell us if it is 1 or 2 or 1 and maybe 2. Yeah, so we still need a little more information. So the next step then is to find the recurrence relation. And what we're going to do now is to substitute Frobenius expansion. So y of x is x to the k times the sum of the power series involving powers of x. And as usual, we require that a naught is not equal to 0. So this is the standard Frobenius ansatz. We differentiate once and twice to get you what we've got here. I put a question here. Why have we used the sum over m when I have previously used sums over n? Now, surely the sum doesn't matter, right, whether it's m or n, but in this case it does. I want you to think about it, or the answer will come soon. Now, so from Bessel's equation, you take these expansions, you put them into Bessel's equation, which is here. And when you're putting in one of those expansions into an equation, it's sometimes easier to use it not in the standard form, which is this one here, but in the form where you have powers of x or some functions of x multiplying the power series, right? If you divide, sometimes divisions can be difficult. In this case, it doesn't really matter. So you put those series into Bessel's equation, you get 0 is equal to, well, I'm not going to read it out to you, but the only thing to keep in mind is that you have 4 terms, and three of them have the same power of x. So if you examine the power of x here and here and here, they are all the same, but this guy here is different. So that's the one which we are going to have to change variables. We need to convert this into a sum over something times x to the m plus k, so it's in the same form as here. Now can you see why I use the sum over m? It's because of this thing here. So we used m we use the sum over m, so in order to differentiate, so to avoid conflict with the n squared term. Yeah, now the n squared, n is some constant in Bessel's equation, and we couldn't have a sum over n for this reason. Of course I could have changed the n squared to m squared, and yeah, but I decided to change the sums itself. Alright, so where are we now? We need to change this third sum so that this power is of the form m plus k. And what you do is, I've kept this as an exercise for you. I hope you can see what's to be done, but and please try it out. Yeah. So once you've done that, you will be able to combine all 4 series into one sum, and this sum will start from 0, and it's going to be of this form. So we have am, 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 but this term which we have modified will have an a of m minus 2 in it. And this whole thing will be multiplied by x to the m plus k. So I've just put a few conditions here. So a naught is not 0, and am is 0 if m is less than 0. That's our standard condition. So whenever we combine these sums, we will end up with some sort of condition on the a's, such that a of m is 0 if m is less than 0. Okay. By the way, this step occurs quite often, so please get the hang of it before you proceed. Now, once again, we use the fact that these x to the m's form is a linearly independent set of functions. Therefore, a linear combination of the x to the m's, if that linear combination is 0 for all x, then we must have those coefficients to be 0 for all m, which means the stuff in the curly braces here is 0 for all m. And I have simplified it here, so going from this step to this one here, so we have am square brackets m plus k squared minus n squared close square brackets plus am minus 2 is 0. Now we have a recurrence relation because we have related am to am minus 2. That means we have a recurrence relation. So the next step then is to find the indicial equation. And for that we need the smallest value of m. In this case it's m is equal to 0, because our sums all start from 0. So set m is equal to 0 in the recurrence relation, and you get a naught times k squared minus n squared, and then we will have plus a of minus 2. But guess what? A of minus 2, this is a negative subscript, so this term is 0. Okay, which leaves us then with a naught times k squared minus n squared is 0. And since a naught is not 0, by definition of a Frobenius expansion, therefore k squared is equal to n squared, or k is equal to plus minus n. Now let's apply Fuchs theorem, because now we have the roots of the indicial equation. We can now complete Fuchs's theorem. So if n is an integer, then the two roots differ by an integer. Therefore we will get a solution about x naught is equal to 0 if we choose the larger root, so k is equal to plus n. But the solution about the smaller root, k is equal to minus n, is not guaranteed. If n is not an integer, then the two series solutions are possible because the two roots will differ by a non-integer. Alright, so that's what Fuchs kind of tells us. Now, before we go on, let's look at the next smallest value of m. We'll see why. Because, okay, if we put m is equal to 1 in our recurrence relation, here's our recurrence relation. If I put m is equal to 1 here, we'll get a1 times some stuff. And here we will get a of minus 1. Now, a of minus 1, this is a negative subscript, so this is also 0. So we have a1 times some stuff plus a of minus 1, which is 0, is 0. Which means a1 times this expression here involving k's and n's is 0. But this expression here in the square brackets is not equal to 0 for k is plus and minus n. You can check this. So the only way for this to be 0 is if a1 is 0. Which means our series solutions will have a0 is non-zero, that's given, but a1 is 0 irrespective of what k is. Now the implication here is that there will be no series involving odd n. Okay, but we'll see that. So now we can develop a Frobenius expansion. We start with the larger root, k is equal to plus n. Write down the recursive relation with k is equal to k substituted with n. So we have am and the stuff in square brackets plus am minus 2 is equal to 0, which gives us an expression for am in terms of am minus 2. Now it's easier, I find it, to deal with an am over here and an am plus 2 on this side. So we change variables from m to m plus 2, and then we get the form which not only do I find it easier to deal with, but it's the kind of form which you will find in Arvkin's book. So am plus 2 is equal to minus am divided by m plus 2 times m plus 2n plus 2. That's our recursive relation. Now we start, as always, with the smallest value of m. M is 0. So we have a2 defined in terms of a0. a2 is minus a0 divided by 2 times 2n plus 2. And I'm going to write this in the following way as minus a0 over 2 squared times n plus 1. Then we put m is equal to 1. If m is equal to 1, you will have a3 in terms of a1, but a1 was 0. So there is no a3, and in fact you can try this out. All odd m will give you a 0. There's no contribution. So we are left with only the even m's. So m is equal to 2. That gives us a4 in terms of a2, and then we can use the expression for a2 which we had above in terms of a0 and put that in so that we have a4 in terms of a0. Now ignore the stuff in blue for the time being. So we'll have a4 is equal to plus a0 divided by 2 to the 4 times 2 times n plus 2 times n plus 1. What we are trying to do is to find a pattern here. And it's not always easy to find a pattern with just a couple of terms. You need a few more. So let's go on. We skip m is equal to 3 because that's an odd term. We take n is equal to 4. This is n, not m. M is equal to 4. And that gives us a6 in terms of a4, but we know what a4 is in terms of a0, so we put that in. And then we get minus a0 divided by 2 to the 6 times 3 times 2 times n plus 3 times n plus 2 times n plus 1. And now we are seeing a pattern emerging here, right? Because I can always have 3 plus 3 times 2 as 3 times 2 times 1. And this I can write as 2 times 1. And above here we can put in a 1. So what we are getting then is something which looks as follows. This can be written as minus a0 times 2 to the 6. Now, the 6 is the subscript of an. That's fine. And then we have 3 factorial, which is 3 is half of 6. And then we've got n plus 3. This looks like a factorial, except it's missing terms. It's missing an n factorial, in fact. So I can write this as n plus 3 factorial and then divide by n factorial, so you get it in the numerator instead. And if you go back, then you can see that the same kind of form can be used. I put it in blue for A4 and also for A2. In fact, this lets us generalize it as for even. I made a mess of the variables here, my mistake. I should have put n, m is equal to 2n, but never mind. So for even subscripts, if it's of the form 2m, then we have a of 2m is given by minus 1 to the m, a naught n factorial divided by 2 to the power of 2m, m factorial, and n plus m factorial. Just check this and see that it works. And this lets us write the power series in this nice form. I really think I need to correct this, but I'm going to make a correction here and then continue the video. Okay, what I've done is fix up this mess between n and m. So I've defined m to be 2 times p, where p is any positive integer. And then we can write a of 2p is equal to this stuff over here, as I explained earlier. So now we have our solution. Our solution y, I've put in subscript n there to indicate that this is the case where we have k is equal to n. So this is the k is equal to n solution. And that's why we have an n there. So we have an x to the n, so that would be x to the k, it's x to the n. And then we have the sum over m now becomes the sum over p, where we have only even terms included. So we have a of 2p, x to the 2p, only the even terms. And we can now put in our expression for a to the 2p, and we get all this stuff over here. And then we have an x to the 2p plus n, where the n is coming from the outside, the term on the outside. All right. Now, there are a few constants here which don't depend on p, so we can pull them out. So we have an a naught n factorial 2 to the n, and then we have written down in these curly braces a series, an infinite series in p. I'm not going to read these terms out to you, but the important part is that the stuff in curly braces is what is the standard definition of the Bessel's function, Jn. So if you pick up Arvkin's book or Riley's book and you look up Bessel's functions, you will find that Jn of x is defined to be this thing in the curly braces. And what's outside is simply a constant. So it doesn't really matter, it doesn't modify the function. So we've got our one solution, and it's the Bessel's function. Now what about the other roots? So k is minus n. If k is minus n, we get another recurrence relation. A of m plus 2 is equal to minus am divided by m plus 2 times m minus 2n plus 2. If n is not an integer, then this will generate a second solution, which is called j of minus n of x. And that's going to be done in exactly the same kind of spirit as we've got jn of x. We'll get the second solution, j minus n of x. The question now is, what if n is an integer? Because if n is an integer, then there will be m such that m is equal to 2n minus 2. That would mean that this denominator goes to 0. And that would mean that a of m plus 2 would be undefined. It would be infinite. So the method of Frobenius would not be defined in this case. And Fuchs' theorem, we should have been aware of this, because Fuchs' theorem did warn us and said that if the second solution might not be defined if the two roots of the indicial equation differed by an integer. Yeah. So if n is not an integer, we will get our two solutions. If n is an integer, we will get one solution for k is equal to plus n, but we will not have our second solution. And that we won't have it because the Frobenius method will not be defined, because these coefficients will at some point become undefined, infinite. So what do we do then? What about the second solution when n is an integer? And here's where we go back to Abel's solution, Abel's method for the second solution using the Wronskian. Now this set I have a tutorial which describes this, so please go back if you've forgotten it. Here's an outline. The outline is as follows. If you've got a second order ODE, y double prime plus p of x y prime plus q of x y 0, then we can define the Wronskian as some constant wa times the exponential of minus the integral of p of x1 dx1. And at that point, I put in a question which I still haven't answered as to why is the Wronskian independent of q. I still don't know why. It depends only on p. Now, once you have the Wronskian, then Abel showed that once you have the Wronskian and you have one solution y1 of x, then Abel showed that you can get the second solution in this way, and we proved this result in earlier recording. So please look that up if you have forgotten where it is, and you will also find this in Untitled Chapter 7. All right, so we have an expression for the second solution given one solution, and let's see if we can use this here. So we're going to start with Bessel's equation with n is equal to 0. 0 is an integer, so we can use this. That simplifies the equation, so it simplifies our life considerably. And we have y double prime plus 1 over x y prime plus y is 0, which means p of x, which is going to go in here, is 1 over x, and q of x is 1. One of these solutions, and I'd like you to check this, is j naught, and j naught is given by, if I ignore constants in front of it, it's 1 minus x squared over 4 plus x to the 4 over 64 minus terms of order x to the 6. Now what does that mean? If you haven't come across this notation before, it means that the smallest error is proportional to x to the 6. Yeah, so we are keeping terms which are of lower powers of x in here. If any higher powers than x to the 4 will go into this error term. So our first solution, y1, is this Bessel's function, j naught. Now we have p of x is 1 over x and q of x is 1, so we need to start evaluating the terms that go into this integral. The first is this numerator, which is an exponential of the integral of p of x. So let's do that. The integral of p of x minus the integral of p of x is simply minus ln of x of x1. Actually, this should be x2 here, because we're integrating to x2. And then we take the exponential of this, so that we get an exponential of an ln, which gives us a 1 over x2. Okay. The next thing we need is 1 over the first solution. So this is the y1. No, too many mistakes in here. 1 over the first solution squared. Now our first solution is a power series, so we need to take we need to find 1 over this power series squared. So I've written it down here, and we use the binomial expansion as in its standard form. We just have to keep track of the terms we are getting. So the binomial expansion says that we have I'm going to treat this whole thing here as our, let's say, a, and now we have a binomial expansion of the form 1 plus a to the power of n. So just to remind you, this would be a 1 plus n times a plus n times n minus 1 over 2 factorial a squared plus dot dot dot. Yeah, that's what I'm using here. So we have minus 2, that's n is minus 2, times this stuff in here. Then we have minus 2 times minus 2 minus 1 divided by 2 factorial times this thing squared. But when you square this term, when you square the first term, you will get x to the 4, which is smaller than x to the 6. That's all right. When you square the second term, you will get x to the 8. So that's now is larger, has a larger power of x than the error term, so it has to go into the error term. And when you multiply these two together, you will get an x to the 6, which is, so all these cross terms and the square of this go into the error term. The only thing that remains is the square root of the first term. Yeah, so we have to keep our powers of x nice, consistent with the error term. And that means that the second, so y1 to the minus 2 is given by 1 plus x squared over 2 minus x to the 4 over 32 plus 3/16 of x to the 4, and then we have our error terms are all proportional to x to the 6 or higher powers of x. We can combine this to get the following. And now we are in a good shape to find the second solution. The second solution will be the first solution, y1 times the integral of 1 over x2 times this power series, where we replaced x by x2, dx2. Integrate it, it's simple, and what you end up with is j0, the first solution, times the logarithm of x plus powers of x. Now, in Rifkin's book, in chapter 7, they discuss how this relates to the standard form of the Neumann function, which is kind of the irregular Bessel's function, y0. I'm not going to bother you about that. That's a nice thing, but have a look at Rifkin's book if you want to find more about it. What I want to point out is, why don't we get the second solution from the method of Frobenius? Because it looks like we have a power series here times another power series, which is j0, except it isn't, because in here we've got a logarithm of x, and so y2 of x contains this logarithm of x, and ln of x does not have a power series expansion about 0. Try it out. You won't get one, and it's nice to find out why you won't get one. It's because of this ln of x that Frobenius's method doesn't work. Okay, so the second solution can be determined. We determine it using Abel's formula for the second solution, and the reason why Frobenius cannot find it is because it contains a logarithm of x. Now, this is quite often the case. In fact, the more elaborate form of Fuchs's theorem will put this in explicitly, but we are not going to be bothered about the mathematically precise Fuchs theorem in this course. So I hope you have got a feel for how you solve the Neumann equation, how we find solutions, and how even when we cannot find a second solution, we are able to use Abel's method to find the second solution, and in doing so we have found that it contains a logarithmic term, which is why we couldn't find it using a power series expansion. Okay, so you will find more about all these topics in Rifkin, Weber and Harris, chapter 7, example 7.6.4, which deals with this particular problem, and Riley, Hobson and Benz 16.4. Please have a look at those books for more information. So that's our treatment of Bessel's function, and I will stop here. Thanks for watching.